So linear momentum. Linear momentum was mass times velocity. An object had to be moving to have linear momentum. Impulse was the average force applied over some period of time, and it was also the change in momentum. So if you had some sort of force applied for a period of time, then the momentum of your object would change. But we looked at situations where the change in momentum of the system was zero. Meaning, basically, the initial momentum of the system equaled the final momentum of the system. Under what conditions was that valid?
If it was conserved.
It worked in collisions, both elastic and inelastic, as long as we looked at immediately before the collision to immediately after. So as long as we didn't worry about any time in there. And it worked for explosions. Basically, it works as long as there was no net force acting on your system. As long as the forces involved in making one object speed up and another object to slow down, as long as the forces were internal to the system, the objects acting on each other, then the momentum was conserved. Same or similar is true for what we call angular momentum. An object that is rotating has angular momentum. Okay? Angular momentum, we use a capital L to represent it. Why, I don't know. I don't know who decided to use L. Turns out, similar to torque, angular momentum can be found by having a lever arm times the perpendicular component of the linear momentum. So for example, the Earth orbiting the Sun. We could find the angular momentum that the Earth has orbiting the Sun. We would need to know R, the radius of Earth's orbit, so how far from the Sun the Earth was. And then we'd need to know the linear momentum, how fast it was moving. So we need its mass, which we'd know. And we can figure out its velocity, because we know how long it takes for the Earth to orbit once. This equation only works if all of the mass is located at the same distance, at the same R, from the rotation axis. So it works fine for the Earth, even though the Earth is a big object. The size of the Earth in comparison to how far away it is from the Sun, the size of the Earth is awfully small in comparison to that. So it's as if it were all the same distance away from the Sun. So that's why this will work. This will work for a hoop, where all of the mass is located the same distance out. We need to modify the equation slightly for objects that don't fall in this category. For example, a pulley. The pulley is a solid uniform mass. As it spins, it has angular momentum. But pieces that are closer to the axis are moving slower than pieces that are further from the axis. So this equation doesn't work to find its angular momentum. The one equation fits all is this. Angular momentum can also be found by taking the moment of inertia of your object times the angular velocity of your object. Okay. That even works in this condition as well. This equation simplifies to this one under these conditions.
That was applicable in all conditions?
This I omega is applicable in all conditions, yes. So I omega works for anything. Turns out impulse. Impulse in terms of angular momentum is an average torque applied for some period of time. And it's the change in angular momentum. If you have a net torque acting on your object, then your object has an angular acceleration. That means it's either spinning faster and faster and faster and faster, or it's slowing down. At any rate, its angular velocity is changing. So you have a change in angular momentum.
Is that a minus sign?
Where?
After changing times?
No, that's an equal sign. There are some conditions in which the angular momentum of the system initially is equal to the angular momentum of the system finally. This will be true in any collision, as long as the collision involves an object rotating at some point during the process. So, for example, if you had a door and you threw a ball at the door, that would make the door swing open, but the door has hinges. So we could say the initial angular momentum of the system, which would be the ball, use this equation for the ball. Even though the ball is not technically moving in a circle, we can still talk about it as if it had angular momentum. L final of the system would be L of the door plus L of the ball. So any collision. Other examples where it works is in a redistribution of mass. Anyone have semi-decent balance skills that would be willing to play for a second? You can only volunteer yourself. You're not allowed to volunteer your neighbors. Anyone? I can't do it by myself. It takes two people. Thank you. So I'm going to have you stand on this platform. It's not the best platform ever, but it works fairly well. I want you to start with your arms out. I'm going to get you spinning, and then pull your arms in. So spin slow. The outside torque was me. It required me to give him a torque to make him spin in the first place. But do you want to do it again? So I have to get him spinning in the first place. But now I'm not touching him. But his angular velocity changed because his moment of inertia changed. By taking those masses and pulling him in, what does that do to the moment of inertia? Decreases it because it's closer to center of mass. If you hold on for just one second, I want to show one more, if you don't mind, since no one else seems excited to participate. Okay. Go ahead and sit in there. Let me get this going for you. Kind of hard to do. Now turn it. Sorry, turn like this way or this way. This one doesn't work quite as well. The wheel has angular momentum. He's changing it by turning it. He's producing a torque. There's an equal and opposite torque that acts on him, which makes him turn in the process. Angular momentum must be conserved. Thank you. So angular momentum of your system initially has to equal the angular momentum of your system finally if there is no external torque acting on the object. So having masses out versus masses in, that's internal to the system. You're the one applying the forces to the mass. Masses are applying forces to you. That's all internal. So the angular momentum of the system, being the masses of the body and the turntable, has to be equal to the angular momentum finally of the system. The reason you spin faster is because your moment of inertia has changed.
Even though in that example where you gave him like an initial push to spin, we're talking just the second you stop pushing him and he has an initial velocity spin.
Correct.
So that's all still internal to the system, so it'll equal.
Yeah, so I gave him angular momentum by applying a torque. So I changed his angular momentum. His angular momentum initially was 0. I changed it because I applied a torque. But once I am no longer part of the picture, once I let go, the angular momentum he has to stay constant. So as he brings his arms in, he spins faster. As I get smaller, omega has to get bigger in order to conserve angular momentum. That's why ice skaters spin faster when they bring their arms in versus their arms out. Okay, I'm sure you've all seen an ice skater at some point in your life. Whether you wanted to or not. That's why divers, I don't know if you've ever noticed, if you've ever watched diving, when they tuck their bodies in really tight, they spin a lot faster than when they keep their bodies out straight. It's for the exact same reason. Okay? When they tuck their bodies in tight, they're decreasing their moment of inertia. The closer the mass is to the rotation axis, the smaller the moment of inertia is. So smaller moment of inertia results in a greater angular velocity, so they spin faster. Gymnasts, the same thing. If you've ever watched the floor routine of a gymnast, they do some flips with their bodies all straight out. They do some flips all tucked up. Same thing, they'll spin faster when their bodies are tucked up than when they're spread out.
Remains the same, right?
The total angular momentum stays the same. Yes. But changing the individual pieces of it. So smaller I means bigger omega to keep L the same.